Greetings and welcome to lecture number 9 on fluid kinematics. So this lecture we will discuss some numerical on types of flow lines. Numerical on flow lines means we have already discussed there are three types of flow lines generally commonly used to describe the flow field. That is path line, streamline and streak line. As far as path line is concerned, generally the Lagrangian approach for Lagrangian approach path lines are used. Streamlines are used for Eulerian approach, and there are equations for path line and streamline as well. Streak lines are only used during the experimental work for visualization of flow pattern. The streak lines are used, that is some dye or color is injected in the flow passage to recognize the flow pattern. So there is no specific equation for streak line. So mainly there are numericals only on the streamlines. So from the given velocity field, how to estimate the equation of streamline, that type of examples can ask. So we'll check the examples. So first example, for a three-dimensional flow, the velocity distribution is given. So x component velocity, y component velocity, and z component velocities are given. What is the equation of streamline passing through 3 points, 1, 2, 2? So that we have to determine. So as per the given data, three velocity components are given. The equation of streamline passing through these points that we have to estimate. So first of all, we can write, as this is 3D flow, we can write the equation of streamline that we already studied. It can be written in different way, but for integration, I think this form is more suitable. Sometimes it can be written as u by dx, that is equal to v by dy, that is equal to w by dz. Both are same, but this is a quite convenient form for solving example because we require integration. Now, only thing is that we can substitute the value of u, v, and w here. So instead of u, we can put minus x, dy, that is 3 minus y, and w is 3 minus z, that is 1, 2, 3. Now, first of all, we integrate 1 and 2, considering these two expressions, and integration will get it. So that is integration of this, that is equal to integration of with respect to dy. So this is log to the base x, log to the base e x, so ln x, that is equal to minus ln y, and it is minus 1, so plus c1. So when considering c1 as a constant of integration, and since the streamline passing through point 1, 2, 2, x is equal to, if you put x is equal to 1 and y is equal to 2, so this is log 1, it cancels, so c1 comes 0. So obviously this expression is x raised to minus 1. So taking anti-log, x raised to minus 1, that is equal to 3 minus y raised to minus 1. Or we can say that is x is equal to 3 minus y. This is the first expression, that is relation between x and y. Secondly, we can equate 1 and 3. So equating 1 and 3, again the similar process we will do. Here only y is replaced by z here. Other integration process remains same. So C2 is again 0 because z is also 2. So the formula, the equation becomes x is equal to 3 minus z. So this is equation number 1. This is equation number 2. So there are two expressions of x. So we can say from 1 and 2 at 1, 2, 2. So the equation is x is equal to 3 minus y, that is equal to 3 minus z. So this is equation of streamline. So the relation between x, y, and z. So this coordinates are given for calculating the constants. So in both cases, the C1 value is coming 0. Some cases it may be non-zero. So this is a type of examples can be asked for streamline. So only from the given velocity field, we have to put this velocity component in equation of streamline and then integrating. First, if it is 3D flow, Then we equate x component with the y, and then x component with the z, and develop a relation. So this way we can develop equation for streamline. Simple type of numericals. Even sometimes the numerical becomes complicated only if the velocity components are complicated. That's it. So the difficulty level increases only with the increasing the difficulty level of integration. That's it. Otherwise, there's no such more varieties are there. Still, we consider this second example. It is for 2D flow now. Obtain the equation for streamlines for velocity field. Now here the velocity field is given, that is 2x cube I hat minus 6x square y j hat. So here x component velocity is 2x cube, y component velocity is minus 6x square y. Now according to the streamline in two-dimensional flow, it is dx upon u, that is equal to dy upon v. Now put the value of uv in this case, not w in this case. So by putting the value of it is dx upon 2x cube, that is equal to dy upon minus 6 square y. So because both cases there is x, so that is the difference in previous example here, because here also x present, here also x present. So we eliminate this. So dy by dx, that is equal to minus 3y upon x. So integrating, we'll get, we take this y this side, so minus 3 upon x. So integration of 1 upon y is ln y minus 3 as it is ln x plus c1. So if we anti-log, that is ln y, that plus 3 ln x, that is equal to c1. Or if we anti-log this, this is y plus, so log is addition of log is after anti-log, that is y into x cube, that is equal to c. So this is the expression of streamline in 2D flow. So this kind of, you can check more varieties. So varieties means only the velocity component procedure remains same. Only the integration part may be different, and sometimes it makes the integration complicated because it is the u component. Generally, inverse ratios are their velocity component. That makes the numerical slightly complicated. Otherwise, the procedure point of view, it remains same. That's it from this session. At the end of this particular session, you should be able to develop the equation of streamline based on the given velocity field. If it is 2D flow, then use this equation of streamline for 2D flow. That is dx upon u, that is equal to dy by v. If it is 3D flow, use 3D streamline equation. And by putting the value of uvw and integrating, we get the final expression of streamline. This is the end of this session. Thank you very much.